Hello, and welcome to this lesson on adding and subtracting numbers in scientific notation. And such a question just says basically that. How do I add or subtract numbers expressed in scientific notation? This could be a very hard lesson. If you watch the previous lesson and the method I used to convert numbers from scientific notation to standard form, this method becomes quite a bit easier. But without that method, this is kind of challenging, especially if you're doing this no calculator. Obviously, if you're using a calculator, you can just throw the numbers in and it's easy. Did you know that the width of a human hair is about this many meters? And a meter, in case you're curious, is about 3 feet. Okay, it's about the size of a yardstick. And that can be expressed in many different ways. So it's this many meters, so 5 times 10 to the negative 6th meters. This many millimeters. Your hair, one hair in your head is about this many micrometers, but it's also about 50 nanometers. And I think that should actually be to the first power, not the second power, so you'd only move the decimal one place. There is no new vocabulary here. Sweet. Move it on. So we are going to learn how to add and subtract numbers in scientific notation. The first thing we're going to start is what happens when they have the same power of 10. So like here, these both have the same power of 10. They are both 10 to the 4th power. So this is the easiest case scenario. This is kind of what we want to happen. And later on in the lesson, when they don't have the same power of 10, we're going to try to get back to this situation so that we can do the math. And really comes down to this. If they have the same power of 10, I'm going to write it as like an up and downy subtraction. You don't have to. If they have the same power of 10, you literally can just do the math with the decimal piece. So here we are going to take that 5.6 and minus that 1.2 just right now. Now I did it up and down because again, I'm trying to avoid using the calculator too terribly much, and well, we can do that subtraction by hand. 4.4. Now our power of 10, we do not subtract that. There's a very common theme you'll see in a lot of different types of math problems. Anytime we have to have the same number to do two things. So like when you're adding fractions, you need like 1/4 plus 3. No, I'm not going to use 3. 2/4. When you add these fractions together, once they have the same denominator, you add the numbers across the top, but you keep the denominator the same. Right? They had to have the same denominator, the denominator stayed the same. Well, it's kind of like the same thing here. In order to add and subtract numbers in scientific notation, they need the same power of 10. But in your answer, that same power of 10 will stay the same the whole way through the problem. All right? That problem's done. Now, one thing we should always check for, and I didn't say it, so I'll say it now. One thing you should always check for is to check to make sure your answer itself is in scientific notation. If it's not, because sometimes it won't be, you will need to do a little conversion like we did in the previous lesson, and then you'll be done. But that problem is finished. That number is scientific notation. Letter B. So I'm looking, they have the same power of 10. I'm going to just line them up because I like doing that. I am adding these together. I know my power of 10 is going to stay the same. So what changes? Well, this part, the decimal piece. I'm going to add those together. I'm going to get a 10.9. And this problem is not done because my answer is not in scientific notation. This number here, this decimal here is too big. You're not allowed to have a 10.9. So we have to do a little conversion, just like we did in the previous lesson. So I'm going to make this smaller by 1 place to make it a 1.09. So if this piece gets smaller by 1, my exponent is going to get bigger by 1. That is our answer in scientific notation. Okay? So you have to have the same power of 10. If they have the same power of 10, you can just do the math with the decimal piece. You don't have to line them up. I like to do that because I'm avoiding using my calculator too much. Okay, again, these could very easily be no calculator questions, so you should be able to do it with and without a calculator. Here are 2 for you to try. So go ahead and pause the video, try these 2 on your own. When you're ready to continue, hit play, and we will go through them together. All right, come on, zoom. There we go. So I'm just gonna write it out. I can see they have the same power of 10. I'm adding together. My power of 10 will stay the same. So now we add. Now when I add it, I'm keeping my decimals lined up because that's how you add decimals. You have to have your decimals lined up. I added a 0, so I have something to add the 3 to. So 3 plus 0 is 3. 9 plus 8 is 17. Carry the 1. 4, 6, 7. So I'm just going to pretty this up because it's a little sloppy right now. There we go. So we got, whoa, what did I do? That's not a 0. That's a 3. So 7.73 times by 10 to the second power. That is scientific notation. So we are done. Letter D. So I'm lining them up because they have the same power of 10. I know my power of 10 is going to stay the same. And now I subtract. Now, this is a situation where writing it up and down doesn't really work. This should stand out as something bad, something we actually can't do just like this. Because you know when you're subtracting, your like 2nd grade, 3rd grade teacher always told you that when you're subtracting, you always put the bigger number on the top. 6.2 needs to be on the top. Well, we don't want to do that because we're actually going to get a negative answer here. And your 2nd grade teacher wasn't planning for negative answers. So this is a situation where using the calculator for the subtraction might actually come in handy. So I'm just going to cheat here. 3.15 minus 6.2. Negative 3.05. Now, if you had to do this by hand, because sometimes you might, all you would do is you would move the 6.2 up top. Oopsie. Like this. And just make sure you know that the 6.2 is the one that's negative. It's a minus that. And then you would get a negative answer. So I could have done it by hand, but, you know, I'll cheat. Now, this might be the very first time we've had a negative number out front here. Is this allowed? Yeah, it's allowed. It's okay. As long as it follows the rest of the rules. Like this is a decimal between 1 and 10. This is an integer. We're good. Oh, not erase. Circle. So yeah. So if you have the same power of 10, you just do the decimal math, and your power of 10 stays the same. So let's expand on that. What happens when you don't have the same power of 10? When your powers of 10 are different, how does that affect our problem? Well, it affects us a decent bit. So really, it's going to add an extra step for us. The one extra step is we need to make them have the same power of 10. So I either need to make this a 10 to the 3rd power, or I need to make this a 10 to the 4th power to make them match. There are times where one way is easier than another. It's really not terribly consistent, but I guess I'll say the best way I've found is I like to change the smaller exponent to match the bigger exponent. That way tends to give me a little bit less work, but it makes no difference one way or the other. you're going to have maybe one extra step if you would change this to a 3. Okay, so I'm going to change this to a 4. So a 10 to the 4th power. So now think, this piece got bigger by 1, so my decimal piece needs to get smaller by 1 decimal place. So to make this smaller, I'm not going to move it this way. That becomes 84. That's bigger. I'm going to move the other way. 0.845. So it moved one place smaller. And there we go. Now I've got two numbers with the same power of 10. I can add them together. And I know I'm going to get the same power of 10. 10 to the 4th. And I was actually seeing if I could do this, the 6.6 plus that in my head, and I think I can. I think it's going to be 7.445. 7.445. Oops, I have the wrong decimal there. Let's try it again. 0.845. 7.445. Ah, I was close. Did I type everything in right? I typed it in wrong again. Look at that. All right, slow down. 6.6 plus 8. Nope. Delete. 0.845. Hey, my head worked and my calculator skills were terrible. So, I mean, I was able to do it in my head. So I just added this decimal piece plus this decimal piece together. I did get 7.445, even though I had trouble with the calculator. And I'm double checking. Is my answer in scientific notation? Yes. Yes, it is. So we're done. Okay. In addition, a subtraction. So I had two numbers in scientific notation. I want to make them have the same power of 10. They need to have the same power of 10. I could not subtract them just like they are. I cannot take 3.1 minus 2.9. That will not work. So to make them have the same power of 10, I'm going to change the smaller one to match the bigger one. That's the method that typically gives you the least amount of work. So I'm going to make this become a 10 to the negative 5th. Now, in order for that to happen, my decimal piece is going to get bigger by 2. So my decimal piece is going to get smaller by 2. 0.031, my decimal place went 2 places, and I think we can agree that this decimal is smaller than that decimal. And now I'm ready to subtract. 0.031 minus 2.9 is going to give me a negative answer, and I know my power of 10 will stay the same. So I can use our calculator for the decimal math, or I could do it by hand if I did 2.9 minus 0.031, and you'd add your zeros, and you'd have to borrow, and let's see, this would go down to an 8, and that would become a 9, and that would become a 10, and we get 10 minus 1 is 9, 6, 8, 2. So 2.869, 2.869. And if we double check using the calculator, 0.031 minus 2.9, we got the same thing. All right, so you can do it by hand. It's possible. We have the ability. We have the knowledge. You also can do it using calculator just for the decimal math. And there we go. Okay, so you need to have the same power of 10 when adding and subtracting. 2 for me, 2 for you. Go ahead and pause the video, try it on your own. When you're ready to continue, hit play, and we'll go through it together. All right, so if we change the smaller exponent to match the bigger one, I'm going to make this a 10 to the 7th power. That exponent got bigger by 1. This decimal piece will get smaller by 1, so it becomes a 0.7. I can add those decimal pieces together in my head. That's going to be a 2.2. My power of 10 stays the same. And the last thing I'm looking for is this actually scientific notation? And yes, it is. That was it. That one's done. Letter D. I'm going to make the smaller exponent match the bigger exponent. That was supposed to be an 8. There we go. So this piece got bigger by 3. My decimal piece gets smaller by 3. So it becomes point something something to 8. There's a bunch of zeros out front. So let's see. 1, 2, 3. All right. So I need to add 2 zeros out front. There we go. And this one can stay the same. So now they have the same power of 10. They're both 10 to the 8th power. Now I can subtract. And I could subtract by hand. I could subtract using calculator. I'm going to use calculator to save some time. You guys should have done this as well. So 3.6 minus 0.0028 equals 3.5972 times 10 to the 8th power. I'm double checking to see if that answer is in scientific notation, and it is. My decimal is good. My exponent piece is good. We're all good. So, same powers of 10 are needed. What about adding and subtracting things that are not even in the same form? We've done 2 things in scientific notation with the same power of 10, with different powers of 10. What if you have a bunch of mixed numbers? So here I have, this is scientific notation, and this is standard form. Well, you've got options. Did you want to change them both into scientific notation? Or do you want to change them both into standard form? Both are okay. A lot of students I see prefer standard form. It gives you maybe an extra step or so. I'll show both methods for this problem. So if you changed this into standard form, so I'm going to make this a times by 10 to the power of 0. That got smaller by 4. This piece will get bigger by 4. All right. He becomes 8, 5, 6, 0, 1, 2, 3, 4. Ooh, I need another 0. So 86,600, or 85,600 plus 34,000. Those are now both in standard form. So I can add them together. That gives me a little over 100,000. 85600 plus 34,000 gives me 119600. Now this would not be done because it does say our answers should be expressed in scientific notation. My answer is not scientific notation. It's standard form. So we would have to then do the extra step of making this scientific notation. Add 10 by 10 to a 0. Put the decimal in the right place, 1.196. This number got smaller by 1, 2, 3, 4, 5 decimal places. So my power of 10 gets bigger by 5 places, giving me to the 5th power. So that's what you would do if you wanted both numbers to be in standard form to start. All right, I'm going to copy this down here, paste image, and then I'm going to erase everything else. So I made a copy of the problem. Now, if you wanted everything to be, if you wanted to go into, get out of here. If you wanted to start with scientific notation first, you're going to save yourself one step. Times by 10 to the power of 0, that becomes 3.4 times by 10 to the, this piece got smaller by 1, 2, 3, 4 places, bigger by 4. And now, see, this one's kind of lucky because they have the same power of 10 to start. They're both 10 to the 4th power. So I can just add the decimal pieces, the 8.56 plus 3.4, and get 11.96 times by 10 to the 4th power. That's not quite scientific notation, so I'd move the decimal over. My decimal piece got smaller by 1 place, bigger by 1 place. We got the same answer. Now, this problem could have been made more complicated. If these did not have the same power of 10, I would have had to make them the same power of 10 before adding. So, there's both ways of doing that same problem. It's kind of up to you. A lot of students do prefer going into standard form, this method here, and that's fine with me. Letter B. So we got to make them the same form. It doesn't really matter to me which way we go. Let's go to standard form because that's what a lot of students seem to prefer. So if I go into standard form, I'm going to make this one become a 10 to the power of 0. So that's going to get smaller by 6. That's going to get bigger by 6 places, becoming 5, 4, 1, 2, 3, 4, 5, 6. Actually, I don't need that times by 10, do I? At least not in blue. All right, so there's my number in standard form. And then 19 million. And I should probably figure out what this number is with my commas. So 1, 2, 3, comma, 1, 2, 3, comma. All right. So I've got 19 million minus 5.4 million. That would give me 13.6 million. That was in my head. This is my calculator. So double checking my head. So that number's in standard form. That is not done because we need scientific notation. So I'm going to make it times by 10 to the 0. I know this can become a 1.36 times by 10 to the something. This piece got smaller by 1, 2, 3, 4, 5, 6, 7 places. So my exponent gets bigger by 7 places. And we're done. So you see this method about getting bigger and getting smaller that I showed you way back in the first lesson that maybe you thought was a little weird. My old teacher never taught us that way. Yeah, but you see how handy it comes in now? Anytime you're doing this converting from one form to another, you don't have to stop and really problem solve. You just have to remember, like if this piece is getting bigger, this piece is getting smaller, and they can be moved together. All right, so there's 2 for me. Here is 2 for you. I want you to pause the video, try these 2 on your own. When you're ready to continue, hit play, and we will go through it together. All right, let us see. So I'm going to change the scientific notation into standard form. So he's going to become a times by 10 to the power of 0. And so he got smaller by 6, bigger by 6, which means 1, 3, and I'm going to move 6 places. So 1 place, 2, 3, 4, 5, 6. Notice I'm not counting zeros. I was counting decimal places. 1, 2, 3, 4, 5, 6 places, comma, comma. So 1,300,000 plus 883,000 will give us 2,183,000. And that was just an in my head. $2,183,000. I just didn't put the 000 at the end, just saving some button pushes. That is not scientific notation, so we are going to make it scientific notation by adding a times by 10 to the power of 0, knowing that this will become a 2.183 times by 10 to some power. My decimal piece got, I was going to say bigger. He got smaller by 1, 2, 3, 4, 5, 6 places. So he's going to get bigger by 6 places, giving us the number 2.183 times 10 to the 6th, and that is all scientific notation, and we are good. Last of this type. Let's do it. Let's make him a times by 10 to the 0. He got smaller by 8. He gets bigger by 8. That makes this a 6, 3, 1, 2, 3, 4, 5, 6, 7, 8. Squeeze it in there. We made it. Plus this 53,000. So we have 630 million plus 53,000. Well, that's going to be 630 million 53,000. Which is not scientific notation, so we're going to convert it back into scientific notation. He becomes 6.3 times by 10. Oh, I guess I actually need more digits, don't I? 6.30053, just to include everything. Times by 10 to some power. This piece got, I almost did it again, smaller by 1, 2, 3, 4, 5, 6, 7, 8 places. So he gets bigger by 8 places, giving us 10 to the 8th power. And we're done. So that's everything you really need to know about adding and subtracting numbers in scientific notation. They have to be in the same form, either both standard form or both scientific notation. In scientific notation, they need to have the same power of 10. If they don't have the same power of 10, you make them the same power of 10. Once they have the same power of 10, you simply just do the math with the decimals. And then make sure your final answer is in scientific notation, and if it's not, you need to do a little bit of converting. All right. A couple little problem solvings, and we're done. Example 4 says a standard CD is about 1.2 times 10 to the negative third meters thick. A thin coating on the CD is approximately 7 times 10 to the negative 8th meters thick. How thick is the CD with the coating added? Oh, okay, so we're just going to add these two numbers together. 1.2 times by 10 to the negative third plus 7 times by 10 to the negative 8th. If you remember, it is usually easier to make the smaller exponent match the bigger exponent, so I'm going to make this become a 10 to the negative third. He is getting bigger by 5. He gets smaller by 5. And 5 smaller is going to be 1, 2, 3, 4, 5. I'm counting decimal places, not zeros. 1, 2, 3, 4, 5 places I'd move the decimal. Plus 1.2 times by 10 to the negative third. And then when I add that together, we get 1.2. I'm adding my head. This 2 would line up with this 0 here. And then I'd have 3 other zeros and a 7. If that doesn't make sense to you, what I did, should be a good teacher. 0.00007. So when you add above these numbers would all be zeros. After this 2, 0, 0, 0, 0, 0, 0, forever. So that would be a 7, 0, 0, 0, 2, 1. Okay, that's what I have down below. So that's what I was doing in my head. And then the power of 10 stays the same. That answer is in scientific notation, so we're done. So that's how thick the CD would be with this coating added onto it. Letter B. The approximate area of the continent of Australia is 9 times 10 to the 6th square kilometers. The area of the continent of Antarctica is 1.37 times 10 to the 7th square kilometers. What is the difference in the areas of the continents? So that word difference means a subtraction. How much bigger? How much smaller? That's a subtraction problem. And when you subtract, you always, well, put the bigger number first, which in our case, 10 to the 7th is bigger than 10 to the 6th. So I'm going to put 1.37 times 10 to the 7th minus 9 times 10 to the 6th. Bigger number comes first. I make the smaller number match the bigger number, so this is going to become a 10 to the 7th. To make that happen, my exponent got bigger by 1. This gets smaller by 1, which makes this a 0.9. That moved my decimal 1 place from 9 to 0.9. And now I can subtract. 1.37 minus 0.9 is 0.47. My power of 10 stays the same. This is not done, though, because that's not scientific notation. This is not scientific notation. We need to do a little converting. For 0.7 times by 10, so the decimal goes here. My decimal piece got bigger by 1. He gets smaller by 1, which makes that a 6. And I guess my answer would be in square kilometers. Okay, so subtraction. Letter C. I would like you to do this problem. So go ahead and pause the video. It says here the population of Washington, D.C. is about 5.9 times 10 to the 5th. South Dakota has a population of approximately 8 times 10 to the 5th. What is the sum of the populations? All right, so now you can pause the video, try it on your own. When you're ready to continue, hit play, and we will go through it together. All right, now as I'm looking at this, both the 5.9 and the 8 have the same power of 10. They're both 10 to the 5th power, which is going to make this very easy for us. Because they have the same power of 10, I can just add the decimal pieces together, which would be 13.9, and know that my power of 10 is going to stay the same. I can see my answer is not scientific notation. My decimal piece is too big, so I'm going to reconvert this. 1.39 times by 10 to the, he got smaller by 1, exponent gets bigger by 1, 10 to the 6th power. You could have also taken both of these numbers and made them both into standard form and then added them and then change it back into scientific notation. It's just a lot more work that way. Letter D. A blue whale has a mass of about 190,000 kilograms. The mass of a whale shark is approximately 2.6 times 10 to the 4th kilograms. What is the approximate sum of the masses of the blue whale and the whale shark? So one more problem for you to try. Go ahead and pause the video, do this one on your own, and hit play when you're ready to continue. All right, so we have that 190,000 plus the 2.6 times 10 to the 4th I showed you before when we did problems like this, we were always making numbers both into standard form. I'm going to do that again here. Why not? So this becomes a 10 to the power of 0. And to do that, my exponent is going to get smaller by 4, so this piece gets bigger by 4. So I'm going, in my head, I'm going 1, 2, 3, 4 decimal places. 1, 2, 3, 4. I made it bigger. 26,000 is bigger than 2.6. It got bigger, and I moved the decimal 4 places. I'm going to add these numbers together and then change them back into scientific notation. So that gives me 216,000, I think. 190,000 plus 26,000 is, 216,000. Changing it back into scientific notation, we're going to add our 10 to the power of 0 and go, okay, I know this can become a 2.16 times by 10 to something. My decimal piece is getting smaller by 1, 2, 3, 4, 5 decimal places. So my exponent gets bigger by 5 decimal places, or by 5 places. And that would be in kilograms is our unit there. Last question. The mass of a white rhinoceros is about 4,850 kilograms. The mass of a hippopotamus is 1.4 times 10 to the third kilograms. How much more does a white rhinoceros weigh than a hippopotamus? Answer should be expressed in scientific notation. Now, if you're looking at this problem, there is one answer choice you can actually cross off immediately, and that's letter A. I know letter A is wrong because it said in the problem our answer should be expressed in scientific notation, and that one is not scientific notation. So it's guaranteed wrong from the beginning of the problem, doing no work. Now, as far as the other two go, or the other 3 options, they all are in scientific notation, so that doesn't help me eliminate any more choices. All right, so now we need a game plan. How do we actually do the problem? Well, this phrase, how much more, that is a phrase that means we're looking for a difference. We're looking for a subtraction. Okay, so we're going to subtract these 2 values together, and then, I guess, change them back into scientific notation to figure out which was the correct answer. So, well, I already have 4850 in standard form. That was the rhinoceros. I'm going to change this into standard form while we're going from here down to here, just to save me a step. So if I make this a 10 to the power of 0, my exponent piece is going to get smaller by 3. The decimal piece would get bigger by 3. Okay, so 1, 4, 1, 2, 1, 2, 3. Yes, just like that. Now I can see that the rhino weighs a lot more than the hippo does. So I'm going to subtract, and that gives me, I'm going to calculate this one, minus 1,400. Actually, I could have done this in my head now that I think about it. It's going to be 3,450. Which means we can eliminate choice B because that has the wrong decimal piece. I know this 3,450 in scientific notation is going to be 3.45, like letters C and D have. Times by 10 to what power? Well, this started with, well, we're going to add our ghost times by 10 to the power of 0. My decimal piece got smaller by 1, 2, 3 places. My exponent gets bigger by 3 places, which makes this to the third power. The answer is letter D, not letter C. So the summary. What is the most important thing to remember when you're adding or subtracting numbers that are in scientific notation? What do you think it is? It should be that you can only add or subtract numbers in scientific notation if they have the same power of 10. And, I guess to throw on with that, a little higher. There you go. They have to have the same power of 10, and your power of 10 stays the same the whole way through the problem then. You do not add a 10 to the 4 and a 10 to the 4th and get like 10 to the 8th or something. That doesn't work, okay? So you have to have the same power of 10, and the power of 10 stays the same the whole way through the problem, including in the answer. Okay. Thank you for watching this lesson on adding and subtracting scientific notation. Until next time, toodles.